Okay, this is from the 2008 AP exam, the free response portion. This is number 1. Concert tickets went on sale at noon, so 12 p.m., represented by t equals 0, and were sold out within 9 hours. The number of people waiting in line to purchase the tickets at time t is modeled by a twice differentiable function, L, for t between 0 and 9. Values of L of t at various times t are shown in the table above. So part A says use the data in the table to estimate the rate at which the number of people waiting in line was changing at 5:30 p.m., which is t is equal to 5.5. Show the computations that lead to your answer, indicate units of measure. So if we look here at this table of values, we see that at each at a given time, whether it's 1 p.m., 4 p.m., 8 p.m., or 9 p.m., this shows the number of people who are waiting in line. Okay, and we want to find the rate at which number of people is the rate at which number of people waiting in line is changing at 5:30 p.m. So we see that somewhere between 4 and 7 would be where 5 is, and we see that here 126 to 150 number of people is going to generally be increasing. So we're not going to be able to get an exact rate of change, but we're only asking about an approximation, so we can just pick two order pairs that sits besides 5. So we'll have 4 126 and 7 150. So we simply find the slope. So the rate of change of people waiting in line is simply change in number of people divided by the change in time. So L of 7 minus L of 4 over 7 minus 4. So the change in number of people is 150 minus 126. The change in time is 3 hours, 7 minus 4. Divide this out, we get 8 people per hour. And so even around 5:30, we're expecting an approximation of number of people still increasing at 8 people per hour. Part B, use a trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours that the tickets went on sale. So the first 4 hours, that means from 12 p.m. to 4 p.m., so from 0 to 4, but it's asking for the estimating the average number of people. So that's using the average value theorem, 1 over 4 minus 0, times the definite integral from 0 to 4 of L of t dt. Now, we're not trying to find an exact value, we're trying to find an approximation. They tell us to use trapezoids, to use 3 trapezoids, add the areas of 3 trapezoids. And if you recall, the area of a trapezoid is width over 2 times h sub 1 plus h sub 2. So between 0 and 4, we can split this up into 3 intervals. Here's the first interval, here's the second, and here's the third. So for the first interval, we see that the width is 1. So 1 over 2 times h sub 1 plus h sub 2. And for the second, the width is 2, so 3 minus 1 is 2. 2 over 2 times h sub 1 plus h sub 2. And finally, the width for the third interval is 4 minus 3, which is 1. So 1 over 2 times h sub 1 plus h sub 2. Okay. And we have our areas of our 3 trapezoids given. We add those together, we get 621, but this is the total number of people waiting in line. So we don't want that, we want the average value, so make sure we have to multiply this by 1/4. So 1/4 times 621 gives us 155.25 people. Okay, would be the average. Part C, for t between 0 and 9, what is the fewest number of times at which L prime of t must equal 0? Give a reason for your answer. Now, it may help to kind of sketch the graph. So what I did was I kind of gave a rough sketch of what this graph may look like. The number of people waiting in line at given values. Now, we see just because 176 is the highest value, that doesn't mean that is going to be the highest, that's going to be the maximum. However, we do know by the pattern of this graph, this is a differentiable function, so it's going to be connected, and it's going to be a smooth curve. So we know that over the course of this graph of this this time period, the graph is going to hit a maximum, it's going to hit a relative minimum, and it must hit another relative maximum simply by looking at the flow of these values. So we know that somewhere between 1 and 4, we're going to get a relative maximum, right? Maybe it is 180, maybe it is 190, but the graph is going to have to come down somehow, somewhere between 1 and 4, because we see the values increase and it starts to decrease. And because of this decrease, it starts to increase again, so we know that there must be a relative minimum somewhere around here. Okay? And I just sketched the graph here just to kind of give a visual representation of what we may be seeing. However, we have to indicate in our reasoning that we don't know exactly where the relative max and relative mins are, but we know generally where it is going to lie. So we have to give a range of values. And see here we have 126 being a relative minimum. Maybe it is a lower value than 126, maybe it's 100 or 110, but we know that it is going to come back up to 150, so there must be a relative minimum somewhere here. And then it goes to 150, goes down to 180, goes down to 80, so we know there must be another relative maximum here. Okay? And so relative max and relative mins would be where our L prime of t must equal to 0. Okay, so because it's a differentiable function and because we know mean value theorem and Rolle's theorem applies, and also intermediate value theorem applies, we know relative max will occur in the interval from 1 to 4 and between 4 and 8. We see those peaks in our values, and also we see a dip in the value, so we know there must be a relative minimum that occur. Our function is differentiable, mean value theorem applies. So there are therefore at least 3 values where L prime of t is equal to 0. Okay, part D. The rate at which the tickets were sold is modeled by R of t. So now we have a specific function that gives us the rate at which the tickets are sold per hour. Based on this model, how many tickets were sold by 3 p.m.? So we simply just take the definite integral from 0 to 3 of R of t. So all this can go in our calculator. Definite integral from 0 to 3 of 550 te to the negative t over 2. We can use the FN integral feature in our calculator to plug in, and we're going to get 972.784. However, they tell us to round to the nearest whole number, so approximately 973 tickets were sold by 3 p.m. Okay, one more problem with 2008, and this is number 2. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. The oil slick takes the form of a right circular cylinder with both its radius and height changing with time. Note the volume of a right circular cylinder with radius r and height is given by v is equal to pi r squared h. So over the course of this time, the radius is expanding, meaning that this oil leak is expanding horizontally as well as vertically. Okay, so part A, at the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeters, the radius is increasing at a rate of 2.5 centimeters per minute. At this instance, what is the rate of change of the height of the oil slick with respect to time in centimeters per minute? Okay, we can go ahead and try and list out all the given information that we have. So radius is 100 centimeters, height is 0.5 centimeters. We know the change in volume of this oil leak is increasing at a rate of 2,000 cubic centimeters per minute. Volume increases. at a here. Okay, and once we have that, we also know that dr over dt, the rate at which the radius is increasing, is 2.5 centimeters per minute. Okay, and then we just want to find dh over dt, find the rate at which the height of the right circular cylinder is changing. Okay, so let's look at our volume formula. V is equal to pi r squared h. Radius is changing, height is changing, so we're not going to be able to replace these variables with a constant because they tell us that over the course of time these variables are going to be changing with time. So if we want to find the derivative that involves two variables and they're being multiplied together, we have to go through a product rule. And this is also related rates as well. So v becomes dv over dt. I'm going to treat pi r squared like the first function and h like the second function. And product rule says f prime g plus f times g prime. So my f prime as the derivative of pi r squared, which is 2 pi r dr dt, times h, that's my second function, plus pi r squared, that's my original f function, times the derivative of my g prime. So h becomes dh over dt. Okay? Now we have all the information given to us. So the only thing that is missing should be dh over dt. We have dv dt, which is 2000. We have r, which is 100. We have dr dt, which is 2.5. We have h, which is 0.5. And then we have r, which is 100. And then we have to square that. All this can plug in our calculator and solve for dh dt. We're going to get 0.038. This is the rate of change of height over the course of time, so centimeters per minute. Okay, part B. A recovery device arrives on the scene and begins removing oil. The rate at which oil is removed is given by R of t, where t is the time in minutes since the device began working. Oil continues to leak at a rate of 2,000 cubic centimeters per minute. Find the time when the oil slick reaches its maximum volume. So the change in the amount of oil in the volume is going to be dependent on two things, right? The rate of change of the amount of oil that is on the scene is going to be dependent on the rate of the leak, okay, minus the rate of the removal. Okay, so depending which one is going at a higher rate, that's going to determine whether this oil leak is going to be increasing over time or whether it's going to be decreasing over time. So the rate of the leak is 2,000, is constant rate of 2,000 cubic centimeters per minute. The rate of removal is 400 square root of t. So what this tells us is that over the course of time, the recovery device will begin to ramp up and begin to become more efficient in removing oil over the course of time. As time increases, we're going to expect this value to keep increasing and therefore eventually, hopefully, overtake the rate at which the oil is leaking. Okay. And part C says find the time when the oil slick reaches its maximum volume. So maximum volume is going to occur when the rate of volume, when dV over dt is equal to 0, right? So anytime we want to find the maximum value, we always set its derivative equal to 0. So if I want to find the maximum volume, I can just take the derivative and set it equal to 0. And that's exactly what we can do. So set dV over dt equal to 0. So now we have a easy equation that we can solve. 400 root t on one side, 2,000 on the other. Divide both sides by 400. Solve for t, square both sides. We get t is equal to 25 minutes. So therefore, and we can also make sure that this is a maximum. So 25 is the critical point. We test 24 into our derivative. We're going to get a positive value. If I plug 26, I'm going to get a negative value. So what that means is dV dt is going to change from positive to negative at t equals 25. So maximum volume is going to occur at 25 minutes. So that means before 25 minutes is up, the oil leak is going to keep increasing because the removal device is not up to speed yet. But once 25 minutes hits, then this removal device is going to overtake the rate at which the oil is leaking, and so therefore we're going to be expecting the oil leak to begin to dissipate. Okay, part C, by the time of the recovery device began removing oil, 60,000 cubic centimeters of oil has already leaked. Write but do not evaluate an expression involving an integral that gives the volume of oil at time found in part B. So in words, what we need to be able to say is volume of oil is the volume of oil on the scene is equal to the initial amount that accumulates before this before the device arrives on the scene, and then plus the accumulated amount at t is equal to 25. So the accumulated amount would be the rate at which the integral of the rate at which the oil is coming in, as well as the rate at which the removal is taking place. And so the integral from 0 to 25 of 2,000 minus r of t will give us the total amount of oil. So if we add up all the oil that's coming in, subtracting all the oil that's being removed, and if we accumulate that over 25 minutes, we're going to get the total amount of oil that is added onto the scene plus the initial amount of oil. So the initial amount plus the accumulated amount will give us the total amount or the total volume of oil.